This project involves training a model to classify digits 0 through 9. Our training data consists of 5,000 digits, the image of 5,000 digits. Each image is a 20 by 20 pixel matrix. And what we do is unwind that into a 5,000 by 401 X matrix. 400 for the pixels, 1 for the bias term. The target vector contains digits of the actual digits. Now the core training of this is regularized logistic regression. I'll post a link to these PDFs. I derived the cost function and the gradient and implemented in MATLAB. Here is without being regularized, and this one is with regularization. And here's the implementation. The output of this function is the cost and gradient. Here's the animation of how it works. For some fixed theta, we are making predictions on each row of our training data and then comparing it to the y-actual. Okay, notice that there's one output node here, so the ones and zeros will tell you whether this algorithm, whether this theta predicts it that it's in this class or not. That animation can be put into this box here. Okay, the output of this box is the cost and the gradient. This gets passed to a optimization function that optimizes theta iteratively. And the result of which is we have a trained vector of weights. In the digit classification case, we're not dealing with a single class, we're dealing with multiple classes so that we have multiple outputs in our model. Therefore, we have to add an additional layer of processing then before passing it to the core functionality. This additional layer of processing involves taking one row of theta at a time and filtering out the y-actual into a binary vector. Here's the animation of it. Okay, first of all, we take the transpose of the theta vector here because the core functionality assumes that theta is a column vector. So each one of these nodes right here, these x nodes, corresponds to a feature. x0 is a bias term. Okay, n is 400, so there's 400 features. There's 400 columns in this x matrix. Each of these output nodes corresponds to a digit class. So is it 0 or not? Is it 1 or not? Is it, and on all the way to 9. So each of these output nodes is associated with some theta vector, and which is part of this theta matrix. We're training one of these columns at a time. Notice that the y-actual gets converted from its original form into a binary form, where since we're dealing with class 0, 1 is a first entry because this is 0, this is not, 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 and this is right here. So is this. So this binary y-actual theta x get passed in iteratively optimized. We do it for the next class, which is 1. Notice that the y-actual is changed also. And we continue doing it for each of the digits. What we end up with is a theta matrix of trained thetas. And that is called all theta in this script, or in this notebook. In the 1 versus all prediction, this function is simple. It just adds a bias term and multiplies the theta matrix by the x matrix, and what we get is a matrix Y of prediction. So this is a sparse matrix. Most of it is 0, and it's one where where the model thinks the corresponding class is. We extend these concepts into a 2-layer model. So each layer is associated with its own theta matrix, and it's being trained the same way. At each layer, a bias term is being added. And I think we can see that here. What function is this? Oh, so I forgot to mention, this is 1 versus all, the 1 versus all function here. Okay, I use a for loop to pass in each column at a time. The optimization function is f minimum cg, so that's something that somebody else wrote. Yeah, I guess the predict function, this is what happens. Okay, just like I mentioned, at each layer we add a bias term, train it, and then do the same thing over here. In the iterative process involves like some back propagation. So whatever this result is, it gets compared to the actual values, and then we optimize theta, I think, each layer at a time.